Welcome to the Deep Dive, where we take on the universe's biggest questions, sift through ambitious research, and extract the crucial insights so you can be instantly well-informed without having to wade through a mountain of sources yourself.
Today, we are undertaking a task that seems, well, utterly paradoxical. We're doing a deep dive into the concept of nothing. We're exploring non-existence itself, how it functions in philosophy, mathematics, physics, and we're drawing heavily on John D. Barrow's exploration of humanity's long, persistent struggle with the void.
And it's funny, the moment you start thinking seriously about nothing, it stops being nothing. It immediately becomes this incredibly powerful, complex, and confounding concept. Our mission today is to unpack why, historically, nothing has been treated by philosophers with anxiety, even repulsion, yet in every field, from math to cosmology, it's emerged as this pivotal something.
That anxiety is really the key, isn't it? Our sources show that the concept of non-existence, of, absolute emptiness, was often treated as this intellectual black hole, a place where logic just failed.
Right.
But the fascinating part, the real story, is how the cultures that weren't philosophically blocked by this anxiety were the ones that unlocked the keys to modern progress.
Exactly. It's the ultimate intellectual hurdle, whether it's mathematicians using zero to build all the other numbers, or physicists creating the first vacuum, or modern scientists realizing the vacuum isn't empty at all. The story of nothing is really the story of revolutionary change.
And we are pulling knowledge from sources that trace this struggle across thousands of years of human thought. We're going to see exactly how our evolving, confusing, and contradictory idea of non-existence of nothing is absolutely essential if we want to truly understand the structure of the universe and, well, how we even came to exist within it.
Okay, let's unpack this. And we'll start at the most fundamental level with maybe the most important revolution in human history that relies on nothing, the mathematical zero. What stands out to you when we look at the history of mathematical nothingness?
What is genuinely astonishing, I think, is just how long it took for a symbol for no quantity to be invented. The zero, whether it's recording the result of, say, 6 minus 6, or just acting as a placeholder in the number 101, it seems utterly intuitive to us now. A third grader gets it.
But its absence just hobbled some of the world's greatest intellectual traditions for centuries.
For centuries.
I always find it shocking that the ancient Greeks, these are the intellectual heavyweights who mastered geometry, developed atomism, invented rational philosophy. They never adopted or invented a proper zero. If they could calculate the circumference of the Earth, why couldn't they handle the concept of none?
Well, the block wasn't mathematical. It was fundamentally philosophical and linguistic. It all stemmed from this profound respect for logic, particularly the kind derived from thinkers like Parmenides of Elea.
Parmenides, right. His argument was incredibly strict about what counts as reality, if I remember correctly.
Incredibly strict. He maintained that you can only speak or even think about what is. For him, thought and being were basically inseparable. Therefore, to speak of non-being, of nothingness, was logically impossible.
Because if you could speak of it, it must, in some sense, exist.
You've got it, which is a huge philosophical trap. If being is the only thing you can discuss, then non-being or nothing can't be a subject for logical development. You certainly can't give it a practical symbol like a numeral. It was this unclassifiable emptiness that just corrupted logic on contact.
And Aristotle kind of doubled down on this, right? He rejected the void on physical grounds.
He did. He was all about classifying and ordering the world. And he argued that since eternal things occupy every place, you couldn't make a physical space or even a concept out of nothing. Treating non-being as if it were a usable, quantifiable thing that you could add or subtract was just. It was unacceptable within their framework. They built an intellectual machine that rejected the possibility of zero on principle.
That philosophical blockage is such a crucial point because it sets up this fascinating contrast with where our modern zero actually came from. So where did the concept manage to bypass those barriers?
For that, we have to look eastward, specifically to the Indian cultures. They possess a deep, robust philosophical acceptance of nothingness and emptiness. For them, it was often interwoven with mystical and cosmological ideas of the void.
So it was more of a cultural difference in how they handled abstraction.
It was, absolutely. Their abstract concept, sunya, which means void or empty or emptiness, it was readily accommodated. The spiritual background made it perfectly comfortable to say that existence could spring from non-existence, or that the material world was just an illusion projected onto some eternal void.
So the leap to creating a numeral to denote no quantity or an empty space was a small, practical one that didn't threaten to, dismantle their entire worldview. They had the philosophical and mystical thread that allowed the zero concept to weave itself into a practical system.
And that symbol then accreted all these philosophical meanings that went way beyond mere accounting. Eventually, of course, it spread via the Arab world. It was a perfect marriage of spiritual comfort with practical need. And the result was revolutionary.
It's remarkable how many names we have for it. Nil, none, nulliform, zilch, zip, nout. We seem obsessed with giving substance to something that's fundamentally absent.
And if you trace the origins of these names, a lot of them are surprisingly pedestrian, especially when they cross over into culture. Take the term love in tennis, which means a zero score. It's so easy to assume some poetic origin, that the scoring starts from a place of purity or something.
But the reality is much more prosaic, according to our sources.
Much more. The term came to English from the French l'œuf, meaning egg. It's nothing more romantic than the round zero shape on a scoreboard.
The egg shape. That makes so much sense. And it gives a new perspective to related phrases. If someone says they are playing for love, it just means they're an amateur, playing for zero financial reward.
Exactly. Or not for love or money implies they won't do something under any circumstances, for nothing.
Okay, so let's trace the lineage of the most famous term, cipher, or zero itself. Where did that journey start?
It started with the Indian sunya, which was translated literally into Arabic as sifr, meaning empty or the absence of anything.
And that Arabic term then embarked on a pretty fascinating word trail through medieval Europe.
It did. As cipher was transcribed into medieval Latin in two main forms, cifra, or the theorem. Cifra became generalized across Europe to mean any numeral, which is where we get our modern word cipher, a digit.
And in a wonderful irony, calling someone a cipher eventually became an insult, meaning a non-entity, a nobody.
There's that philosophical anxiety popping back up. The symbol for nothingness carries negative cultural weight.
It really does.
But the second term, zephyrom, that's the one that gave us our modern name. It was shortened in the Venetian dialect of Italian to zero as we use it today. It's just a wonderful example of how a concept initially resisted so violently gradually became indispensable, forcing the language itself to accommodate it.
And that transformation happened not just because it was linguistically convenient, but because of the immense revolutionary mathematical power that the zero symbol finally unleashed.
The foundational mathematical breakthrough that really necessitated the zero was the invention of the positional or place value system. This is the system where the location of a symbol determines its value. The difference between a 1 and a 10. It first appeared in Babylonia around 2000 BC.
And positional notation is what makes all of modern arithmetic possible. I mean, just imagine trying to multiply numbers using Roman numerals. It's utterly impractical. The positional system lets you use way fewer symbols to represent infinitely large numbers.
Absolutely. It was incredibly efficient.
Yeah.
But the crucial missing piece was a symbol to mark an empty location. If you write 16 and then you want to write 106, you have to indicate that there are no tens. It's genuinely baffling that it took over 15 centuries to move from a working positional system to an explicit, usable zero symbol.
So when the Babylonians did introduce it, it was just a separator.
Yep.
What was the key limitation of their symbol, the double chevrons, compared to the Indian concept?
The Babylonian zero functioned only as a placeholder. It was an accounting tool. It let them distinguish, say, 60 from 1. But, and this is the crucial part, it was never used as the answer to a subtraction problem like 6 minus 6.
Ah, so it couldn't stand on its own?
Never. It was just a utilitarian marker of an empty space. It lacked the metaphysical, abstract notions of nothingness that the Indians brought to the table. They were just being very efficient accountants, not deep mathematical philosophers.
So the Indian zero was the first symbol that was mathematically complete. It could stand alone as a number indicating no quantity, allowing arithmetic to fully flower. Now, let's pivot to how modern mathematics manages to construct something truly profound from this mathematical nothing, the empty set.
The empty set, symbolized as that circle with a slash through it, A. It's defined simply as the set that has no members. It seems like a tautology, but it's absolutely foundational. Logically, it's a subset of every other set, including itself. And this simple concept is where set theory creates something genuinely profound from nothing.
I think a lot of us just take the existence of numbers for granted, but this system shows how we literally build all of arithmetic starting from zero.
That's right. Zero is defined as the empty set, A. Then the number 1 is defined as the set containing 0. The number 2 is the set containing 0 and 1, which is A, and so on.
That's so counterintuitive for anyone who thinks of math as, counting apples. You start with the concept of nothing, the empty set, and you systematically use it to generate every single positive integer that follows. Nothing is the absolute base, the fertile ground from which all positive structure emerges.
It is the ultimate intellectual purification. And this elegance extends to more advanced concepts like John Conway's surreal numbers, where the number 0 is created by choosing both the left and right sets to be the empty set. The mathematical void isn't just useful, it's genuinely productive.
But while mathematicians were embracing nothing, physicists and philosophers were struggling with the idea of a physical void for centuries. And that brings us to our next major struggle: the search for, and the ultimate creation of, the physical vacuum.
The ancients, particularly in the West, had this immense intellectual and, well, visceral fear of emptiness. The feeling was encapsulated by the term horror vacuum, nature's abhorrence of a vacuum.
As we've established, Aristotle rejected it because he believed eternal things occupied every place. If a void existed, it would have to be a place where nobody could be. And that just flew in the face of his systematic view of the cosmos.
And this rejection of the physical vacuum was dominant throughout the early Middle Ages. This was especially true for the intracosmic void, a vacuum within our experienced universe. Thinkers believed that if you somehow created a physical void, nature would instantly rush in to fill it.
And this wasn't a physical law of pressure, it was teleological. It was the idea that matter moved to fill the void because it intended to prevent non-existence.
Exactly. But the sources note that the debate got a bit more sophisticated in the 14th century, particularly around the extracosmic void.
The void beyond our universe.
That's right, the vacuum beyond our perceived finite universe. This concept started to gain some credence, but it became tied up with immense theological stakes. The belief was that the space beyond the known universe was infinite, indivisible, and completely filled with the infinite presence of God.
So if you proved the existence of an extracosmic void that was just empty space, you risked reaching a heretical conclusion about the very nature of God's omnipresence. The physical vacuum was deeply dangerous territory to be exploring.
The religious and philosophical stakes meant that for 2 millennia, the dominant view was that a perfect vacuum was just impossible to create. No experiment could succeed because nature would always intervene.
That doctrine finally crumbled in the 17th century with the rise of experimental science, and the shift from teleology, nature's intentions, to measurable physical laws started with a pretty mundane problem: suction pumps.
In 1638, Galileo observed that even the best suction pumps could only ever raise water about 10.5 meters high. No matter how powerful the pump, that was the limit. This observation was absolutely critical because it showed that nature's abhorrence of a vacuum was, well, limited.
That limit implies a finite, physical, quantifiable cause, not some universal philosophical principle. I mean, if nature truly abhorred a vacuum, why would it stop its abhorring precisely at 10.5 meters?
Galileo knew this limit meant there must be some physical force at work, and he proposed a sort of finite strength of the void. But it was his student, Evangelista Torricelli, who solved the puzzle completely in 1643.
Right. Torricelli theorized that the column of water wasn't being sucked up by the pump.
It was being pushed up by the weight of the air, the Earth's atmosphere exerting pressure.
And he proved it using mercury, a liquid that's 14 times denser than water. A heavier liquid would require less atmospheric pressure to hold up a column.
Precisely. He calculated that the mercury column would stand at a much more manageable 76 centimeters high. His experiment was simple, profound, and revolutionary. He filled a long glass tube with mercury, inverted it into a basin of mercury, and watched the column drop. And it stopped right at 76 centimeters, leaving a measurable visible space above it.
The Torricellian vacuum, the first sustained physical vacuum ever created. It immediately proved that the fear of the void was misplaced. It wasn't an impossibility, it was just a region protected by atmospheric pressure.
And this led directly to Blaise Pascal's crucial mountain test in 1648. If the column was held up by the weight of the atmosphere, Pascal predicted that if you took the setup up a mountain, you'd reduce the weight of the air above it, and that would cause the mercury column to drop.
His brother-in-law, Florent Perrier, carried out the experiment on Mount Puy-de-Dôme, measuring the column at the base and then again at the summit, 1,465 meters up. This was the definitive proof.
The result was undeniable. The column dropped by 8.25 centimeters at the summit. This not only proved that air pressure decreases with altitude, but it basically established the structure of our own planet's atmosphere, that it thins out into the empty expanse we now call space.
And finally, the true public spectacle that drove home the massive power of atmospheric pressure came from Otto von Guericke in 1654 with his Magdeburg hemispheres.
This was a piece of dramatic public science designed to shock the skeptics into submission. Von Guericke took two large, hollow bronze hemispheres, about 20 inches in diameter. He joined them together, used an air pump he'd invented, and sucked the air out, creating a vacuum inside.
And then came the horses.
The image is just iconic. He had two teams of 8 horses, 16 horses in total, pulling in opposite directions. And the tremendous pressure exerted by the surrounding atmosphere was so great that the combined teams failed to pull the two pieces apart.
It's an incredible demonstration.
It visually proved that far from shunning a vacuum, nature defended it strenuously, because the powerful something, the atmosphere surrounding the nothing, the void, was holding the hemisphere sealed with tremendous force.
So these experiments successfully banished the philosophical horror vacui and moved the scientific world toward explanations based purely on matter and motion. But this created a new paradox for the next great thinker, Isaac Newton.
While the vacuum was being validated on Earth, Isaac Newton was trying to define the mechanics of the entire cosmos. He needed a stable environment for his laws of motion, which led him to this concept of absolute space.
Absolute space. This was supposed to be this unmoving, fixed, imaginary background stage, an ultimate reference frame against which all movement could be objectively measured.
It was crucial for his theories, but it was unobservable and, frankly, deeply uncomfortable to him philosophically. Because if space was absolutely empty, he ran into a massive problem: action at a distance. How could gravity or light transmit instantaneously across billions of miles of nothing?
He famously wrote that it was inconceivable that inanimate brute matter should operate upon and affect other matter without mutual contact.
This is what necessitated the introduction of the ether.
Yeah.
The ether was this hypothesized, extremely dilute, subtle, invisible fluid that filled all space. It was the medium that allowed light waves to travel and somehow mediated gravity across the void.
And Newton himself was incredibly conflicted about its nature. He went back and forth between viewing light as particles and waves, and he struggled continuously to explain gravity with it. He even suggested the ether might be sparser inside dense bodies, which would cause objects to move toward areas of lesser ether density, effectively explaining gravity.
The need for a mechanical explanation, something touching something, was just so ingrained in scientific thinking that even Newton couldn't entirely shake the ghostly hand of the ether. The assumption remained: there must be something filling the void.
And this conceptual confusion over the ether persisted for 2 centuries until we get to the famous Michelson-Morley experiment of 1887. This was designed to finally measure the Earth's movement through this stationary ether, the so-called ether wind.
The theory behind it was simple physics, and it relied on this great analogy of a swimmer in a flowing river. It's really key to grasp this.
Okay, let's break that down. So you imagine a river flowing quickly. A swimmer tries to make 2 round trips of equal length. One is straight across the river and straight back, and the other is swimming downstream and then turning around to swim upstream back to the start.
And if the river is flowing, the round trip across the river and back, perpendicular to the flow, is always quicker than the path that goes downstream and then upstream. The upstream journey is slowed so much that it dominates the total time.
So the time difference between the 2 routes reveals the speed of the river.
Exactly. And Michelson and Morley designed their interferometer to do exactly that, but with light. If the Earth was moving through a stationary ether, then light rays traveling on perpendicular paths should take different amounts of time to complete their round trips. This would create a measurable interference pattern, revealing the speed of the Earth relative to the ether.
But the astonishing outcome, repeated over and over, was a null result. There was no difference. Light traveled at the exact same speed in all directions relative to the Earth, regardless of the Earth's motion.
This was just catastrophic for classical physics. The conclusion was undeniable. The hypothesis of a stationary ether is erroneous. The Earth wasn't moving through a medium at all. So if the ether didn't exist, what was light traveling in? And why didn't movement affect its speed?
This crisis led to a kind of intellectual desperation, right, which resulted in the frankly bizarre rescue attempt by George Fitzgerald and Hendrik Lorentz.
The amazing shrinking man hypothesis.
Exactly.
It was. Well, it wasn't derived from physics, but was forced by the result of the light experiment. Fitzgerald and Lorentz suggested that the only way to mathematically explain the null result was if objects moving at high speeds physically contracted in the direction of motion, just enough to cancel out the expected time difference in the experiment. It was a mathematical fudge, a profound one, but it seemed absolutely crazy.
So the stage was set for the ultimate realization of nothing. Enter Albert Einstein in 1905, who solved the problem not by introducing some strange new physical effect, but by fundamentally revolutionizing our concepts of space and time themselves.
Einstein just abandoned the entire Newtonian apparatus of absolute motion, absolute space, and absolute time. His special theory of relativity rested on two simple postulates, but the second one completely rewrote our understanding of the vacuum.
The first postulate was that the laws of physics are the same for all observers moving uniformly. What was the key second postulate about nothingness?
It was that the velocity of light in empty space must be measured to be the same constant value by all observers, regardless of their own motion. By simply declaring the speed of light a universal constant, the entire need for a mechanical medium like the ether just vanished. The void was truly empty, and it could transmit light without any supporting structure.
So if the speed of light is constant, then that Fitzgerald-Lorentz contraction, the shrinkage, was no longer a bizarre physical hypothesis to save the ether. It became a simple, unavoidable mathematical consequence of his new laws of space and time.
The vacuum was finally achieved, at least theoretically. Space was mathematically empty, yet capable of conducting light and gravity through geometric curvature. It was a profound intellectual victory over that long, persistent anxiety about the void.
And Einstein himself acknowledged his debt to the experimentalists. He later said that without Michelson's marvelous experimental work showing that the ether didn't exist, relativity would today be scarcely more than an interesting speculation.
A fitting tribute. But here is the massive, dramatic irony of the 20th century. Just when classical physics had finally succeeded in purifying space of all material content, quantum theory stepped in and filled it right back up again.
This is where our deep dive into nothing gets truly counterintuitive. So we spend millennia trying to prove the physical void is possible, and finally we achieve it with Einstein. And yet, quantum mechanics comes along and insists that perfect emptiness cannot exist.
That is the central shock of modern physics. The vacuum is not a serene, empty stage. It is fundamentally dynamic. Even the founders of quantum theory, Schrödinger, Heisenberg, Bohr, they were themselves staggered by the implications. It brings to mind Richard Feynman's famous quote, "I think I can safely say that nobody understands quantum mechanics."
And the reason the vacuum can't be perfectly empty lies in the uncertainty principle, Werner Heisenberg's foundational discovery.
The uncertainty principle dictates that certain complementary attributes of reality, like a particle's position and its momentum or its energy and the time over which you measure that energy, cannot be known simultaneously with arbitrary precision. There's an intrinsic limit to how much we can know.
Okay, so let's apply that restriction to the vacuum. If the vacuum were perfectly empty, we would have perfect knowledge.
Precisely. If it were perfectly empty, we would know its position was zero everywhere, and its energy would be exactly zero. That perfect simultaneous knowledge of both zero position and zero momentum or energy is fundamentally forbidden by the uncertainty principle.
The system has to retain some fundamental indeterminacy. The quantum rules require that the vacuum possess some irreducible minimum energy.
That's where the last stand of the uncertainty principle manifests itself, in what became known as the zero-point energy. The vacuum must be energetically dynamic to avoid violating the fundamental rules of quantum mechanics. It cannot achieve perfect rest.
And this concept of zero-point energy, or ZPE, is the minimum irreducible basic energy that is always present, even at absolute zero temperature. So the vacuum is no longer empty, but the lowest energy state available. A seething, energetic sea.
And this idea moved from just a theoretical necessity to experimental proof with the Casimir effect, which was predicted in 1948. If the quantum vacuum is seething with these ZPE fluctuations, we should be able to interfere with them and measure the resulting force.
Okay, so the setup is pretty elegant. You take two perfectly conducting parallel plates, put them extremely close together in a vacuum.
And the plates exclude certain wavelengths of these ZPE fluctuations. They're energy waves that are just too long to fit between the plates, kind of like a standing wave on a guitar string.
So because certain energy wavelengths are excluded between the plates, you have more vacuum fluctuations, more ZPE energy waves on the outside of the plates than on the inside, which creates a quantifiable pressure imbalance.
And that imbalance generates a tiny but measurable force pushing the plates toward one another. The Casimir effect proved definitively that this basic level of electromagnetic oscillation, this minimum zero-point energy of the vacuum, is real and has real physical consequences.
The source material provides a brilliant analogy for this, drawn from nautical history to help us visualize the force.
Yes, the maritime Casimir effect. Historically, sailors knew that when there was no wind and only a strong sea swell, two very large sailing ships rolling parallel to one another would inexplicably be drawn together and risk a collision.
And the mechanics are exactly the same as the quantum effect.
Exactly. The waves that roll between the ships are altered, and they often cancel out, reducing the wave energy in that confined space. The higher pressure exerted by the open sea waves on the outer sides then forces the ships together. The tremendous power of the vacuum pushing those plates together is basically a gigantic subatomic version of two ships being pushed together by the pressure of the open ocean.
So if the vacuum is the lowest energy state, it is certainly not passive. It's better described as a hive of activity, or a constantly simmering sea of virtual antiparticle pairs.
Right. For example, electron-positron pairs are constantly appearing and then vanishing back into the void.
How is that possible without violating energy conservation? I mean, doesn't creating mass and energy out of nothing violate the most fundamental rules of physics?
This is where the uncertainty principle acts as a regulator, or maybe more like a cosmic banker. Energy can be borrowed from the vacuum as long as that borrowed energy is repaid fast enough. It's an energy loan arrangement.
So the more energy you borrow, the more massive the virtual particle, the quicker it has to be paid back.
Exactly. The particles exist for such fleeting moments that they're fundamentally unobservable, but their cumulative effect is absolutely real. And this is proven through a phenomenon known as vacuum polarization.
Vacuum polarization. This is what happens when you place a real stable particle, like an electron, into this virtual sea.
Yes. The electron, being negatively charged, instantly attracts the positively charged members of the virtual pairs, the positrons. They temporarily gather around the electron.
Forming a kind of positively charged shield or cloud around the bare negative charge of the electron.
Right, and this cloud effectively polarizes the vacuum around the real particle. And this leads to a phenomenal consequence. The strength of the electromagnetic force itself actually changes depending on the energy of the interaction.
How so?
Well, imagine a low-energy particle coming in to interact with our electron. It only feels the weaker, shielded charge. The cloud acts like padding. But a really high-energy particle, one with enough momentum, can penetrate that positive shielding cloud, get a much closer look at the bare negative charge, and thus feels a stronger, unshielded force.
And this was experimentally verified, which proved that the quantum vacuum isn't just theoretical. It actively dictates the effective strengths of the fundamental forces we observe in nature.
And now we take this energetic quantum vacuum, this universal energy field, and we apply it to the largest possible scale, the entire universe. The weak nature of gravity is relevant here.
Right. Gravity is the weakest force by far, 10 times weaker than electromagnetism. But it dominates on astronomical scales simply because mass and energy only come in a positive, attractive variety, unlike charges, which can cancel out.
When Einstein formulated general relativity, he introduced a constant, the cosmological constant, lambda. He needed this term to force his equations to describe the static universe he believed in. It acted as a ubiquitous anti-gravitational force to counterbalance the attraction of gravity.
He famously called it his greatest blunder after the universe was shown to be expanding, thinking he missed the most profound prediction of his own theory. But lambda, or the idea of a pervasive cosmic energy, it didn't disappear.
Far from it. Modern cosmology suggests that lambda represents a ubiquitous energy field that increases in prominence as distance increases, and it's interpreted as the energy density of the vacuum itself, pushing space apart.
The latest observations from tracking distant supernovae provide strong evidence that the expansion of the universe is actually accelerating. And this acceleration is attributed to the presence of a non-zero vacuum energy, the lambda force, which we now commonly call dark energy.
So we've come full circle. The vacuum, once thought to be an embarrassing void, is now this massive cosmic energy field driving the universe's ultimate fate. But this leads us directly to perhaps the greatest unsolved problem in all of physics, the vacuum energy problem.
This is where the numbers become truly insane. If we calculate the zero-point energy contribution to lambda based on what we know from quantum theory, we should be able to predict the density of dark energy.
And the quantum prediction is utterly gargantuan. It predicts a vacuum energy density so high that the repulsive force would be 120 orders of magnitude, a factor of $10 than the observed value.
I just need to stress the scale of that error for you. If you asked for an inch of string and the calculation gave you the distance to the nearest star measured in light years, you would still be less wrong than this calculation. It is the largest mismatch between theory and observation in the history of science.
The observed value of lambda is fantastically small, requiring an almost unbelievable fine-tuning. We have to ask, why is the quantum zero-point energy, which should be driving expansion at an insane rate, almost perfectly canceled out, leaving only this tiny residue of energy, the dark energy we observe?
And the existence of life itself hinges on this fine-tuning.
Absolutely. The source highlights that the universe needed billions of years for gravity to pull matter together into stars, galaxies, and complex molecules to allow life to form. This required the repulsive force of the vacuum to be fantastically close to zero.
So universes that contain life must be big and old, dark and cold.
Exactly. If our universe was less of a vacuum, if that repulsive lambda force had the massive predictive value, it would have flown apart instantly. It could not be an abode for living complexity.
The fact that nothing is not entirely nothing, but rather this dynamic, fine-tuned field that dictates our reality, is the central mind-bending insight of this entire exploration.
And the scientific struggle with nothing has gone hand in hand with human exploration of the void in art and culture, often reflecting that same fundamental anxiety, or, on the other hand, a profound fascination with its potential.
We see that conflict beautifully illustrated in the concept of horror vacui when it's applied to art, particularly Islamic art.
Yes, Islamic traditions generally rejected the idea of leaving blank spaces. Instead, artists filled every single surface with intricate, infinitely repeating geometric patterns, tessellations, that seemed to extend forever.
This aesthetic impulse was deeply theological. The idea was that since God alone was considered infinite and perfect, human art could only direct the mind toward that infinite perfection. By creating finite segments of patterns that were obviously meant to be infinite, they treated the void not as emptiness, but as a challenge to be filled by endless repetition and complexity.
And then, in stark contrast, 20th century Western art became fascinated with nullachrome, the limiting process of reduction. Artists deliberately explored the concept of reducing color, content, and form to test the very boundaries of representation itself.
We're talking about pieces like Ad Reinhardt's 5-foot square all-black canvases, hailed by some critics as an ultimate statement of aesthetic purity, or Robert Rauschenberg's all-white canvases.
These pieces forced the viewer to confront the boundary between a painting and a concept. Were you looking at nothing, or were you looking at the ultimate representation of the canvas itself? They explored the philosophical idea that maybe the purest form of art is the one that approaches the aesthetic analog of zero.
And musicians followed this road to nothingness too. Most famously John Cage with his composition 4R33 Rao.
The composition consists of exactly 4 minutes and 33 seconds of total, intentional silence. The performers are on stage, but they play nothing. Cage intended it as the musical analog of absolute zero temperature where all motion stops.
But of course, as the source notes, absolute silence is impossible. The listener always hears ambient noise, the rustling of clothes, the sound of the air conditioning, their own heartbeat.
So even in the deliberate attempt to create an artistic void, the environment, the vacuum, is instantly filled with the noise of existence. The medium remains dynamic.
And while philosophers were often paralyzed by the paradoxes of nothing, writers and dramatists just embraced them. What was heresy to a logician was a massive gift to an author.
Shakespeare, in particular, was a master of using the ambiguities, the puns, and the double entendres of nothing. In plays like Much Ado About Nothing, the title itself is a double entendre on female chastity and the triviality of gossip.
But the most profound use comes in King Lear, where the destructive theme is introduced by Cordelia's famous line to her father, "Nothing, my lord, nothing." And Lear replies with that terrible, ominous prophecy, "Nothing will come of nothing. Speak again."
That sets the stage for the play's ultimate theme of reduction. Lear's daughters strip him of his status, his security, his entourage, having and having his remaining power, until one asks, what need one? The fool later reduces Lear even further, calling him an O without a figure, a non-entity, a zero.
That image of the O is key. Shakespeare was exploring both the negative side, absence, denial, bad consequences, and the positive side. The circle, the O, was also associated with the shape of the egg and female potential. It symbolized both emptiness, the zero, the non-entity, and the creative power inherent in the whole and the whole.
It's a powerful realization that centuries ago, writers were using the same concept of nothing as a metaphor for destruction and creation that modern physics uses to describe the beginning and end of the universe.
And these linguistic gymnastics and cultural explorations waned in philosophy after the 17th century. Thinkers following Galileo just distrusted contemplating words when physical experiments were proving so fruitful. But the fundamental philosophical question remains.
The ultimate riddle raised by Leibniz in 1697 that still plagues us today. Why is there something rather than nothing? We have only managed to prove that nothing is so hard to achieve that it seems easier to have a universe of something.
We began this deep dive seeking to understand the nature of nothing, and we discovered that to study it is to study nearly everything fundamental about our reality. The journey has taken us from the Indian concept of sunya all the way to the bizarre physics of the quantum vacuum.
We trace the concept of zero, which originated in the East as this beautiful confluence of pragmatic accounting and spiritual emptiness, to the classical physical vacuum, which required spectacular public experiments involving Mercury and 16 horses to prove its existence against millennia of philosophical resistance.
And the physical void, once established by Einstein as a mathematically pure space devoid of the ghostly ether, was immediately filled again by 20th century quantum theory with zero-point energy and virtual particles. The concept of nothing constantly flips itself into a dynamic, energetic field.
And the ultimate fate of the cosmos now hinges on that quantum vacuum. Our very existence depends on the cosmological constant, lambda being extraordinarily fine-tuned, ensuring the repulsive force of the vacuum is fantastically close to zero, allowing the universe to become big and old enough for life to form.
So the key insight we take away is that nothing is not the absence of everything. It is a complex, active state that drives progress precisely when it is viewed as a potential something. The quantum vacuum isn't inert. It is the source of all mass, all forces, and all acceleration in the cosmos.
And this leads us to one final, deeply provocative thought that builds on the dynamic nature of the quantum void. Our sources explore the ultimate paradox of existence and non-existence through black holes, the ultimate expression of something, the region of infinite density and gravity.
Right. We know, thanks to Stephen Hawking, that black holes slowly evaporate, and this is due to quantum vacuum fluctuations right near the event horizon.
The extreme gravity pulls apart those virtual antiparticle pairs that we discussed, turning one into a real particle that escapes. That's the Hawking radiation, at the expense of the black hole's own mass and energy.
So the vacuum, the ultimate nothing, is slowly consuming and destroying the ultimate something, the black hole.
So if the quantum vacuum can destroy black holes, regions where gravity is so strong that nothing, not even light, should escape, what does that imply about the final reality of nothingness itself? The energetic vacuum state might be the only true eternal constant, patiently transforming the things we perceive as concrete, stable existence back into energy.
The struggle to define non-existence continues to define reality. We encourage you to continue exploring the strange relationship between the quantum void and the cosmic scale.